Hey there, and welcome to the fourth video in the Battleship-Noir series. Today we're going to be talking about some background on the game Battleship, how it's played, and how the inspiration for the ZK implementation came about. Moving on from there, we will take a look at the project structure, how our repositories are organized, and how they all relate to each other in making up the entire application. And then finally hop into a demo of the front end without diving into the code, but explaining where each technology that was gone over previously is used. But let's go ahead and jump in and give some background on the game Battleship. So the game Battleship is a two-player adversarial board game. It works by each player being given a 10 by 10 grid and 5 ships that they place at their discretion on the grid. A key aspect of the game is maintaining incomplete information. You do not want to share your ship positions with the other player. If a player were to gain your ship positions, then they'd be able to win the game very quickly. But the way the game works is both players will place their ships and the game will commence. A player will take their turn by specifying a coordinate based on the X and Y coordinates provided from A to J and 1 to 10. And if their shot is reported back from the other player as a hit, then they will place a red peg on the adversary board. As you can see right here, this is your board, this is a view of the adversary's board, with the key fact being that none of their ships are visible. But anyways, so a red peg will represent a shot, and if it is reported back that you have missed, then a white peg will represent that miss. But you cannot take a second shot at the same coordinate once it's been made. The game concludes when one of the players has sunk all of the other ships. And Battleship is a perfect example for demonstrating how incomplete information games can be enabled on Ethereum. Prior to this, if two players want to engage in a battleship game, all ship positions would be exposed on chain, but using zero-knowledge proofs, we're able to mask this information and thus enable fair adversarial competition without compromising key data to the game. So moving on to the project structure of Battleships-Noir, it's made up of 3 separate repositories, the first one being the core repository. And this is where we maintain our smart contracts and Noir circuits. We also have a front-end repository that contains the React application, hosting the front end for our proofs. I want to mention real quick that each one of these repositories has an extensive README for enabling setup and also making it easy to follow along how the circuits work and what technology is being used. The last repository to go through is the subgraph. And for those who aren't familiar with subgraphs, they are a way to specify what event data we want to track for a smart contract. So looking at their website, thegraph.com, the graph network allows you to specify events that you want to track on a smart contract and then expose that event data through a GraphQL API like so. And the alternative to this is if you want to get data on a smart contract, you'd make numerous RPC calls, but you can imagine this would be very inefficient over large data sets. So instead, using the graph, we can make a single HTTP request and get all this data back in one return, which makes it much more efficient than calling smart contracts directly. And without this, we really wouldn't have the current infrastructure and usability we do for BattleZips. And with that, I think it's time we jump into a demo. So we'll go ahead and start the app locally. Open up the Battleships-Noir front end. And as a React app, we simply start it by doing yarn start or npm start. Okay, so this is a look at the application. Just real quick, we have a wallet login right here using Web3 modal to allow MetaMask connection as well as Taurus on the Gorilla network. So we start the app and we're greeted by a menu. We have a few options here. One is to start a new game by hosting it. Option 2, option 3 are to join game, join random game. Obviously, There are no open games right now, so we can't do that. So we will go ahead and start a game real quick. Actually, let me go back real quick. One thing worth mentioning is that these open games are going to be fetched from our subgraph. We're simply looking for games that are in a started state and have not been joined by another player yet. So now we are prompted to the new game view, and we will have a nice ship selection here. So we can go ahead, select a ship, and then hover over and choose where to place our ship within valid board boundaries. Now we can start the game. And when we click start, it's going to generate a board proof to ensure that board state is valid. And then after that, it will call a smart contract function to actually create the game. You can see now we've been prompted in MetaMask. And all these calls are going to be made to our main Battleship game contract. And we'll go over our smart contract infrastructure more in video 6. Okay, so now we can see we have started a game, waiting for an opponent. One thing to note here is that this Ethereum symbol indicates whose turn it is. So when an opponent joins the game, it will allow us to take a shot. And then once we take a shot, the Ethereum symbol will go to the opponent's side, indicating it's their turn. Let's go ahead and switch accounts real quick. And we can see here the subgraph is now fitting in that this is indeed an active game. So let's go ahead and join. Again, same idea, we're just placing our ships. One thing worth noting though is this is not going to be stored on chain. As of right now, all ship placements are stored in local storage, which isn't the most ideal setup, but to maintain the decentralized nature, it's the way that worked best in this initial implementation. Further down the road, we may look to store a ship state in a decentralized network such as Ceramic, decentralized data storage layer. Another valid option could possibly be GunDB, but for right now, we're sticking with local storage. I will warn you though, when you clear your cache, your ships might disappear. And in that case, you just want to leave/forfeit the game. Okay, so the same deal, we generated a board proof and now we're attempting to join an active game with ID 8. All right, and now we have joined the game. We can see here the Ethereum symbol is on the opponent's side, so we can't make our turn yet. We have an option to leave a game, in this case forfeit because we're in an active game with another player. But yeah, let's go ahead and start playing. Rejoin. Okay, so since it's our turn, this hover symbol is popping up and we can take a shot on the 10 by 10 grid. Go ahead and fire. This is going to generate, or I'm sorry, this first shot will not generate a proof because generating the proof is dependent on reporting shot validity back. So whether or not a shot has hit your ship or not. So the first shot is not going to actually generate a proof for that reason because there's nothing yet to report. When you make a return shot, though, you're going to be reporting that previous shot. So for every shot after this, we will be generating a proof because we have that report to make back. Okay, and we can see that shot came through. It actually hit one of our ships. But just before going any further, one thing worth noting is that all of this shot data is being fed in by the subgraph. As right now in this current version, it's the most efficient way to maintain game state and fetch it again quickly. It does have a notable shortcoming though, which is that it will oftentimes, due to the load on the graphs network, take longer to update than the actual chain state. So sometimes you can take a shot, the transaction will go through, but you'll still be waiting for the confirmation on the game view. But unfortunately, that is just one of the shortcomings we have to put up with now. Let's go ahead and return a shot, and we can see this return shot did indeed generate a proof. We're now being prompted by the smart contract again. All right. Awesome. So we can see that that previous shot we made, which made impact with the ship on the other board, the fact this is a solid circle colored in with red means we did have a successful shot. And if we miss, then we'll simply see this X on the board for shots taken. But yeah, I think that is a good place to wrap up. We could play through an entire game right now, but due to the nature of blockchains, it'd be very slow and not practical for this demo. But looking ahead, when recursive proofs are implemented in a future version, we'd plan to play this entire game over a state channel, thus eliminating the wait time between moves, instead of waiting for transactions to settle. But with that, that wraps up today's demo. And looking ahead to the next video, we're going to do a walkthrough of the Noir circuits we implemented, give a line-by-line explanation, and also explore some of the design considerations made just due to the current state of the language. But thank you for sticking around for video 4, and look forward to seeing you in video 5.